Increasing, decreasing. So notes open, increasing, decreasing. Yesterday we related whether a graph is increasing or decreasing based on the sign of who? It's not on this page, let's see if you remember. The sign of its which derivative? First. Why is that so important? Can a function have more than a first derivative?
Yes.
I can have a second or a third or a, well, it can keep on going unless it becomes what? Do you remember that word? Unless it becomes indifferentiable or zero. So if the derivative is zero, what's the next derivative?
Zero.
And the next, okay, so do you remember what that's called? Trivial. Trivial. If the derivative becomes trivial, then it doesn't really matter either. Okay, anyway, the sign of the first derivative. So, question. Let's double check yesterday, really quickly, the example that we ended on. You said this graph was increasing from 4 to 5, which means the slope of the tangent lines for that entire interval, x interval, the left being 4, the right being 5, all of the tangent lines should be what? Sloped how? Uphill or downhill?
Uphill.
Uphill, because they should have what kind of slope? Positive. So let's check it out. Here's 4, here's 5. Let's go up here. Are all the slopes positive? Yep. Are some of them higher and some of them lower? Yeah. But are they all sloped up? Yes. Hey, I can make an evergreen tree. They're playing Christmas songs on HGTV. I can do it. How about 6 to infinity? Are all the slopes positive? Yes. Yes, they are. Some more positive than others? Yes, but they're all sloped up. Decreasing. How about negative infinity to 1? Are those all negative? All of them? Yes, some more negative than others, but all of them are negative, right? 1 to 4, same dealio. 1, graphing little baby tangents. Question, kiddos. There we go. I'm trying to make an actual line. There we go. Why did we have to split it up at 1 again? Isn't it decreasing for this entire time? There's a vertical asymptote. And if I included 1, I would be saying, hey, 1 works. But does 1 work? No. So I have to split up at discontinuities, okay? And then there was one more place where the graph was negative, which was 5 to 6. Now I'll finish my Christmas tree. Okay? Are all those slopes negative? Yeah. Yes, they are. There you go. Does that make sense? So, increasing, decreasing. Let's go a little bit further into it. Ready? From pre-cal, quick recap. That's why it's in green. And I think we actually talked about it this year once or twice. So far. For a graph to be strictly monotonic, it's only doing one thing. Meaning, strictly monotonic, it's either completely increasing or completely decreasing. Either completely increasing or completely decreasing. You also say strictly increasing or strictly decreasing. How can you remember that? Remember? Strictly monotonic, only increasing or only decreasing? Oh. Yeah, right? It's only doing one thing. Monotone.
I remember last year we used the example of my brother on HCTV.
I forgot about that. That's really funny. Oh, John. Now, if a function is strictly monotonic, and if we were talking about how the sign of the derivative shows whether a function is increasing or decreasing, then if a function is strictly increasing, what's going to be true about its derivative? Only positive. Or if a function is strictly decreasing, what's going to be true about its derivative? Only negative derivative. Now, before we move on, can you guys be creative for a second? What? Math class on a Tuesday? Can you think of a function, just in general, let's not apply it to a derivative yet. Can you think of a function that's only positive? 2x, but I can plug in a negative 5, that's negative 10, or a positive 5, that's 10. X squared. Oh. Okay, so hold on. Only positive. We could say either absolute value of x, or we could say x squared. Let's do x squared just for sake of simplicity. So, an example of a derivative that's only positive. Now, hold on. If f prime of x equals x squared, then the original function f would only be increasing. Why? Because all the derivative values, whether it's at 1 or -5 or 5 or -10 or 10, all the values are going to be positive of the derivative. Now, can anyone be amazing? We haven't done any integration this year. Ooh, this is snazzy. But can anybody think of going backwards, if the derivative is x squared, what would the original function have been?
1/3 x cubed.
It's an x cubed, and why does there have to be a 1/3? Because the 3 comes down and has to cancel because he's not there. Ooh, that's fun. Our first exposure to power rule backwards. How can you always check if you've done it right? Derive it, yeah. Bring down the 3, it cancels, and you get x squared. So what's a function that's strictly increasing? A cubic function. A basic cubic function. Does that make sense what we know about the cubic function? Oops, that wasn't a very good cubic function. Not every cubic function, but a basic cubic function. Is he strictly increasing? Yes. Now some of you are like, there's a 0 right there. There's a horizontal tangent right there. True. But this does not count as being constant. Do you guys know why? It's a point. I said it yesterday a few times. I was trying to get it ingrained in here. If the derivative is 0 at one point, does not mean that the function is constant. If it's 0 for an extended interval, then it's constant. But if it's just 0 at one point, let's do an example. Ready? Derivatives can be like rates, right? Instantaneous rates of change. Like a cop with a radar gun and seeing how fast you're going, right? Okay. So, if velocity is positive, if the derivative is positive, that means I'm moving from your perspective to the right. Okay? So I'm moving, I stop. I'm moving. Question, did I ever start going the other direction? No. Was I constant at any time? No. Like if I had been parked here for a while at a stoplight or something, yeah, okay, I'm constant, I'm not moving, just chilling, my velocity is 0. But if I'm just going, I do a momentary stop and I'm going. Think of a baseball. It has a positive velocity, a momentary 0, and then a negative velocity. But you don't see that baseball just frozen in the air and you're like, it's 0. And then it drops, right? That's not realistic. So, we can say with motion or with functions in general, if there's only one point where it stops, you just say it's increasing the entire time. Now question, can anyone think of a function similarly that's strictly a derivative or a function of a derivative that's only negative? Ooh, that's complicated to go backwards though. Anything else besides negative absolute value, but good job. I just don't want to go backwards with that one. Negative x squared? You guys are boring. Alright. Can I do negative e to the x? Does that work? Okay. Let's do something more exciting. So what if f prime was equal, let's make it g, right?
That's way more exciting.
There are way more letters in the alphabet than f. Okay, is that always negative? Because e to the 2 is positive times a negative. E to the 10 is positive times a negative. E to the 0 is 1 times a negative. E to the 1/2 is still positive times a negative. Those are all negative. Question. What would the original function have been? Careful, not e to the negative x, because this should have been e to the negative x again. Good idea, though. Negative e to the x. Does that make sense? The negative just stays, derivative e to the x is e to the x, so it doesn't really matter. So what's true about negative e to the x? That's e to the x, swoop up, being flipped down. Oh, is he strictly decreasing? Why am I showing you these things? Just to remind you of what it looks like for a function that can only be positive or a function that only can be negative, and what a graph would look like strictly decreasing or strictly increasing. Okay. At the very bottom of the page, now that we've talked about strictly monotonic, boring functions, just kidding, functions that behave only one way, we need to talk about one more quick little thing. So what if a function is not strictly monotonic? What if it sometimes increases and sometimes decreases? Maybe it's even sometimes constant, but that's really rare. And the functions will do that. What if it's not strictly monotonic? Sometimes it's increasing, sometimes it's decreasing. Okay, so what does that mean? Its derivative is sometimes careful, careful. A function is sometimes increasing, sometimes decreasing, which means its derivative is sometimes positive or negative. Maybe it can be both. Well, if it's not strictly monotonic, strictly increasing or strictly decreasing, the derivative has to be able to be both sides. Kind of like, Katrina, you gave me one that's a good example for this one. Ready? She said, what about, let's do h of x, the h prime. She said 2x. Why is that a function that's sometimes positive and sometimes negative? Give me an x, any x that makes it positive. 2. 2 times 2, 2 times 1, 2 times 10, 2 times 100, 2 times any positive number is positive. What could make it negative? A negative number, right? Okay, so the derivative can sometimes be positive, sometimes be negative. Where is this one coming from? Nice. And what does x squared look like? And how does he behave? How does he change? How does he move? He decreases, and then he increases. But the question is, where did the change occur? When did the change occur? At the vertex. But we're not just dealing with parabolas, so we can't just keep the word vertex. That's not going to be helpful. We're dealing with cubics and quartics and ln's and etas and fractional stuff and trig. So, critical numbers. Why? What's going on at the vertex? What's going on at any relative minimum or relative maximum? Either the slope is 0 or, wait, absolute value. What else could the slope be and still have? Or undefined. Critical numbers have a pitchfork. Why? Because there are two different types of points at which the sign can change. So, where? At critical numbers. Any other place? Let's see if we missed anything. We'll see if we missed anything. First of all, increasing, decreasing test. We've been talking about it for a while.
Yeah.
Increasing, decreasing test. Increasing or decreasing test. How do we know if a function, if a thingamabob, whatchamacallit, is it? How do we know if a function is increasing or decreasing? Based on the sign of f prime. No space. I'm not going to fill in anything. So if f prime is greater than 0, well, okay, here's the one thing I could write, Ryan, that some people will like. Some of you hate inequalities. You can also say is plus. It's not very grammatically correct, but is plus. Is positive. Or if f prime is, what does less than 0 mean? Is negative. And then you guys don't need the last one because it equals 0. Okay? So if f prime is positive, f is increasing. If f prime is negative, then f is decreasing. Do positive and increasing mean the same thing? No! Do negative and decreasing mean the same thing? No. Just be aware. But as you guys keep writing, I'm going to zoom out. I'm going to go get a rounded box and make it yellow. Rounded box. Boop. Make it yellow. Boop.
I thought you were actually getting out a yellow box.
Oh.
I was like, that's so cool. I wonder if she's gonna do with it.
We're up to 23.
I wish I was that cool. I think we're up to 20.
Are you gonna make like the
Or
white
I'm
box?
four.
Or 20?
You guys double check. It is 24, right?
Make that equal.
No, I haven't updated it.
And
It's 24.
Hold on.
Otherwise, formatted like that have to fit in the yellow box.
At the very bottom it says, watch out for discontinuities. Wait, what? But we just said critical numbers. What's the big deal with discontinuities? Well, we're leading up to something. Corey, stay alive, bud. I know it's rough. But we have to watch out for discontinuities because. I'm going to give you a quick example of a function that is not strictly monotonic and that does not change at a critical number. What? I'm going to give you an example of a function that is not strictly monotonic but changes from increasing to decreasing at something other than a critical number. How's that going up, going down? What about f of x, I'm not giving you the derivative, I'm giving you the function, equals 1 over x squared. Wait. can't be 0, but question, where does the graph change behaviors? Ooh. Doesn't just have to be a critical number, does it? What's it doing from negative infinity to 0? Increasing. What's it doing from 0 to infinity? Decreasing. What's going on in between? Not a critical number. A vertical asymptote, right? So we have to be careful not just of critical numbers to split up functions to analyze their behaviors, but we also have to be careful for discontinuities. That's the one exception. Huh? Oh, it's a vertical asymptote. VA adds 0. Sorry. Yeah, it looks kind of funny. Maybe it looks more like a U or something. V. Okay, so to help us out, to prepare for, we got to watch out for discontinuities. We're going to talk about all the different possible domain problems, or at least the most obvious ones. Pre-cal review. You guys ready? Give me something. How does a domain get messed up? How do I find a discontinuity? Poles and or vertical asymptotes which both occur when you have a
0
denominator. Is that okay? Denominator can equal 0, and if you need some sort of actual visual of that, right? If I have f of x over g of x, girls focus, my domain, g of x, whoever he is, can't be 0, right? All the zeros of the denominator are going to be discontinuities. Square roots! I'm going to say even-powered roots, remember? There technically can be any even-powered roots. Even-powered roots are only real with positive arguments. And how does that appear as far as domain problems? If I have a square root of some sort of function, f has to be greater than or equal to 0. This is what you usually forget. Are you allowed to have square root of 0? Yeah, square root of 0 is just 0, no big dealio. But am I allowed to have square root of a negative number and have it be real? Not really. Number 3. You're welcome. Number 3. Oh, come on. What? Logarithms. Nice. Logarithms. Thank you, Corey, for translating. Not translating. Projecting, thank you. Logarithms must have, what? A non-zero positive argument. What does that look like? A lot like the even-powered roots, but different. If I have any logarithm, base b, of a function, or you can think of if I have any natural log, because he's the one that hopefully we'll see more, because we don't like the normal logs because they have yucky derivatives. Whoever is inside, bless you, must be greater than 0. 0. Good? What else?
Jumps in like a piecewise?
Yeah, maybe. Domain problems. I'm going to make that number 5, though, piecewise functions. Who is he? You guys have to help me out. No, because E's good, right? He's smooth.
Jumps.
Tangent.
Trig. Which trig? Tan of somebody. Secant of somebody. Cotan of somebody. See. Cosecant of somebody. Sine and cosine are okay, yeah? Domains. X cannot equal. I'm cheating. Why? We have different vertical asymptotes depending on the functions, right? Tangent is sine over cosine. Secant is 1 over cosine. They have the same denominator, so remember, for these ones, cosine can't be 0. Oh, so my angle or my argument can't be, let's see, cosine can't be 0. Cosine is 0 at pi over 2. So it can't be pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2, or negative pi over 2, negative. Okay, so there's a lot. We're not going to write it. But tangent and secant both don't exist when cosine equals 0. And cosecant, 1 over sine, and cotangent, cosine over sine, both won't work when?
Sine equals 0.
Exactly.
Whoa.
Look, we don't have to memorize all kinds of craziness. We just have to kind of know the idea. The denominator can't be 0. Piecewise functions. Ooh, come on, AP number 1. By the way, if you were absent yesterday, that is due today. Have it in my hands. Give it to me before you leave for it to be on time. But number 5. How is a piecewise function discontinuous besides whether it has a square root or a denominator or a logarithm or trig?
There's a jump at a second.
Watch out for jumps at separators. So, hold on, this might help some of you because some of you are really, really bad at piecewise functions and figuring out whether or not they match up, whether it's an original function for continuity or its derivative for differentiability. So what if I was to give you something like f of x is equal to g of x for x less than or equal to a. Look at me generalizing for you. Technically, you would probably see it a less than x, but either way. Oh, that's okay, let's do it. It's too messy there. Who's the separator? A. He's in both. He's separated, one piece from the other. How do I check to see what's going on? Maybe I shouldn't do domain. Maybe I should say continuous. Ready? Check the one side, check the other. How do we check the one side? Plug it in to the one side. How do I check the other side? Plug it into the other side. It doesn't matter whether it's or equal to or not. I'm checking the one-sided limits as you come from one side or come from the other. You don't have to equal if you're coming from a side. And we're asking ourselves the question, are they the same? If it's continuous, they're equal. If it's not continuous, they're not equal. Is that cool? Okay. So maybe that's a good sum up after our AP number 1 that was due yesterday. Kiddos, all of that was to talk about discontinuities. Pourquoi, pourquoi, how come? Why were we talking about discontinuities? Because we need to analyze a function. And we start by finding discontinuities.
Thanksgiving dinner suddenly moves up like 3 hours.
It's always both. You have like Hispanic, white, and Arab side. It always comes over.
What's like Arab?
All the custard. It's like there's this basic equivalent for Arab is not now. It's like it's called
What day is Thanksgiving?
Huh?
What day is Thanksgiving?
Thursday.
No, like the day. The 24th.
Guys, you better be ready. My non-multitaskers. Are you gonna have a tofurkey or are you actually going to a church?
A tofurkey?
That's
not real.
No, that's everybody.
Everything
That's so
is
true.
real.
That's the one heard of a tofurkey.
I've
Have
heard
you
this.
heard
I've
Have you had a
heard of
tofurkey?
No.
But wait,
Really?
oh my gosh,
I'm gonna have a little.
I bet it's really good.
I'm scared. Really like it.
But out of all the things to have,
I
that's
like
like
ham. How do you taste ham?
honey bee cam.
It's Thanksgiving, so.
Aw.
Like, what are the points of turkeys are really wide? I tell people that I don't back out.
I like green.
That's
I like
like, that's literally
Yeah.
all of them.
No.
That's so sad.
Keep writing, keep
You
writing.
like mashed potato?
I'm just being really gracious because you guys don't pay attention when you write anyway, as you can tell. But we need to talk about this in a second, so keep writing.
That happened to me after a while. I don't know what happened.
They look like your same type.
Yeah, it just happened. Oh, I got a really bad ear infection for some reason. Oh, I got like a little sick at the end. And I got an ear infection. I got to the hospital, and then it got really bad. So I went to the hospital. I gave me penicillin for it. I'm allergic. Penicillin. I literally my entire body was hot. It was so disgusting. Yeah, it looked sad.
Are we almost there?
No,
I'm number 2.
I'm on T.
Honestly, I've actually.
I'm on 3B.
Brandon finished, you should all be done.
What? You know what?
Okay, keep writing. Don't stop, you get frustrated. It's okay. As you guys are writing, number 1, big thing, discontinuities. If you were to box important stuff. Number 1, discontinuities. Number 2, critical numbers. Number 3, sign chart. Basically. That's the dealio. My oar is misplaced. I don't really know why. Hold on. If you notice that, I apologize. Why are there people in the hallway? I don't know. Somebody didn't want to teach today. Just kidding. Oh, it was the pup.
There's a dog?
Where did not
The dog who always comes.
Oh, it's a dog.
Trinity drops a dog.
She's ready to go.
No,
It's not Miss Gunn.
Oh my gosh.
If we're allowed to have that dog here, we're just allowed to have his dog here.
Mr. Carmichael's sister's dog is the cutest dog I think
You
I've
know whose
ever
dog is
seen.
actually
The
the
lab.
best
Well, you
My
know
dog is so
they're training
annoying.
him for guide dogs.
She fell asleep during church once and she started snoring and I almost like convulsed her.
Then sometimes it just like starts like ringing. You're like, oh.
That made me cry.
Mr. Carmichael, his mom and sister do like guide dogs in America sort of thing, so they always have dogs in church. Alright, you guys ready? Here we go! Woo! Number 1! Alright, those of you still ready, you better be extra quiet because then I'll not mock you for taking forever. Number 1! Just kidding, I don't mock. Discontinuities! It's okay, you mock me too. Discontinuities. Find the domain and continuous problems, and we just talked about them all. Number 2, solve for the first derivative and find critical numbers. Oh, that's how you find critical numbers. You solve for the first derivative. So, what's the pitchfork remember? What's the pitchfork stand for? Set the top equal to 0 when you find the actual zeros of the derivative, and then set the bottom equal to 0 when you find the DNEs of the derivative, or the undefineds, right? And both of them are critical numbers. True? However, really quickly, the DNEs compare to the discontinuities. Why? If a function has a vertical asymptote at a value, it's probably going to have an undefined derivative at that value too, but it never existed to begin with. Interesting. Which is why for critical numbers, the very first step is that the function must exist at each of the points before you think about it being a critical number. Number 3, sign chart. Mark intervals with domain problems and critical numbers with what? Oh, with all the ones from number 1 and from number 2. Put the x values from number 1 and number 2 in the sign chart. Test a point for each interval. I think we did something last year with testing a point from each interval. By plugging into the, I would box it or underline it twice. Plugging into who? The first derivative. Why? Because the sign of the first derivative tells me the increasing or decreasing nature of the original function. The sign of the first derivative tells me the increasing or decreasing nature of the original function. Theoretically, this should probably be a forever card, but it's way too long. So let's go ahead and just get really used to it. I'm going to change this slide soon. If you want to take a picture to keep writing, you may. My ones who are not doing math, shame on you. This is what makes homework and tests harder. 5, 4, 3, 2, and... There's no graph! You're not allowed to graph it! How on earth can we figure out whether it's increasing or decreasing? This isn't pre-cal anymore. You use your calculus skills. And what are your calculus skills? What you just wrote down. Step number 1, discontinuity. Do we have any? Hey, can we be super specific? Is it a whole? Why is it not a whole? Look at me trying to trick you. Why is it a vertical asymptote? It does not reduce. Remember? Holes are removable. Holes can be factored out. Vertical asymptotes are stuck. Oh, okay, there's a vertical asymptote. So therefore the domain, remember, x cannot equal 1. You guys got it? Denominator equals 0, x can't be 1? Yeah. Okay, we found our discontinuities. Number 2, what are we going to do? Find our critical numbers by taking our derivative, bottom d top, minus top d bottom, all over bottom squared. See why we're saving this function? Sorry, this section until we already did lots of derivatives? The derivative is one little baby piece of the whole thing. We end up with, let's see, x minus 1 minus x, right? Yeah. Which is negative 1. What are critical numbers? Can the top equal 0? Nope. He's just a number. Can the bottom equal 0? Not 1 and negative 1. Careful. Just set this equal to. Square root both sides. X minus 1 equals 0. Oh. What's our critical number? 1. Oh. So far, we have our domain, we have our discontinuities. Why did I put an extra note on this one? Is it a critical number? Yes, but why am I saying vertical asymptote? Because it doesn't exist to begin with. There's not going to be any sort of relative min, relative max, relative anything at this point because it doesn't exist. It's a vertical asymptote. Step number 3 says, okay, take all the numbers that you've compiled. There's only one of them. And make a sign chart. And mark whatever numbers you found. And you only found 1. Literally, the number 1. Right? Now, here's how we test. Ready? This is my shortcut version. There's a whole table in the book. You can check it out. He's a good one. Just, I'd rather shortcut it because I'm preparing you for an AP where you have limited time. On top, I want you to tell me what's going on for the derivative in this interval, in each interval. And then on bottom, I want you to tell me what's going on in the function for this interval in this interval. And how do we do that? Your steps say pick one test point and plug in to each. Kind of. Pick one test point. So what's the test point on this side of 1? 0. So if we go ahead and plug in and say, hey, whose f prime is 0? Where's f prime? Here he is. 0 minus 1 is, that's a positive, and then a negative. That's a negative. All I need is a negative sign, because that tells me what's f doing that entire time. Decreasing. See it? And then I go ahead and pick some number, any number over here. I'll pick 10 just for sake of illustration. And if I plug in 10, 10 minus 1 squared, 81. Oh, it's a negative 2? Yeah. So what's going on with this function, cool kids? Strictly decreasing. But how would we say the strictly decreasing nature? Oh, negative infinity to infinity? No. How would we say that? We can say strictly monotonic, except, hold on, careful. Why are we going to have to state 2 intervals and not just 1? The vertical asymptote. So I have to split it up at the 1 because at the 1, remember, I have a VA. You want to put a little dotted line and be like, oh, I gotta split it. And I end up with negative infinity to 1 and 1 to infinity. Now there's a lot more that we could do with our calculus skills, but based on what we've already written, we're going to stop there. Does that make sense what I did? Step 1, check for discontinuity. Step 2, check for critical numbers. Step 3, mark however many you have. Check the sign by picking any number. Plugging in, the sign will be the same for the whole interval because it can only change at critical numbers and discontinuities. And then put your conclusion down below. Cool? What test are we using in order to do this again? Technically just the increasing, decreasing test for functions. You kind of think of maybe some of the theorems as well. But let's keep going. Oh no! Ready, set, go! Follow the steps 1, 2, and 3. Just a hint, number 1. Does a polynomial have any discontinuities? No. He's good. This derivative isn't too bad either. This is a function we could have only guessed at last year. We would have had to do some sort of crazy, find all the different possible zeros, and big division, long division, nastiness to try to factor them. Calculus is so much fun. Calculus, it's so much fun. And remember, in order to put a number on a number line, all you need to know is approximately what it is. You don't have to know exactly. Yeah. Set each factor to 0. Factor first, and then each factor to 0. What's that number 2?
I just did negative 10, negative 1, 1.
There is no bottom, right? So we're just setting the whole thing for these. Make it easier, you could even pull out 4.
Positive, negative, positive.
Step 3 is where it gets a little tricky. Check out what I'm about to do. That's what we're doing. All right, cool kids. Discontinuities. Your answer was none. Domain is all real numbers if you want to think of it that way. Totally cool. Step number 2, you were supposed to find your derivative, which was Equals 0. Why? Because we're solving for the critical numbers. Why not a pitchfork? Because it doesn't have a bottom, right? But to solve anything equal to 0, don't we always factor? So our critical numbers, ooh, we have some this time, are going to be at x equals 0 plus or minus root 5. Cool. Step number 3, what do we do with all of, well, we don't have any from there, and then, oh, okay, our critical numbers from there. Where do we put them? On a number line. Yeah, basically the sign chart is a number line, right? And we're going to try to plug into f prime, start top to bottom, plug into f prime to figure out how f is behaving. Now help me out. Negative root 5, oh that's disgusting. But what's something definitely on that side?
Negative 10.
Negative 10, for sure. Maybe something closer. You just have to pick something. So what if I was to plug in f prime of negative 10? Check the sign only. Don't plug in there, that's complicated. Plug in here. Negative 10 times 4 is a negative. And negative 10 squared is 100 minus 5 is a positive. What's a negative times a positive? See what I did? I didn't get a number. I just got a sign. We did that with limits, right? Check the sign. So then I know this one is going to be negative, hence, for this interval, negative infinity to negative root 5, f is decreasing. What's a number that's definitely in between negative root 5 and 0? Negative 1, right? So f prime of negative 1. I'm just guessing, we're probably going to do f prime of positive 1 and then f prime of positive 10 just to make everything easy and symmetric. Because it seems to be centered around 0. When you guys plugged in negative 1, what did you end up getting?
Positive.
A positive. Good, I agree. Hence, the function must be increasing. Now, I'm not saying it's linear. I'm just saying it's going up. When I plug in 1, it's going to be negative. Just by plugging in. And then when you plug in 10, it's going to be positive. So how can we state our conclusions? I can say f is increasing on and decreasing on. What would be my intervals for increasing?
Negative square root 5 to 0.
Negative root 5 to 0. Union with?
Square root 5 to
Root 5 to infinity. How do you know that? Because you look and say, hey, once increasing, always increasing on the interval split up by critical numbers and discontinuities. These are the only places it can change. So if I do one test value, it's true for the whole interval. And decreasing is going to be the other one because x is within negative infinity to negative rad 5 or 0 to rad 5. Dun, 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 dun. Now question. Think about what you know about a polynomial of 4th degree. If we look at this and we say, hey, it's decreasing, then increasing, then decreasing, then increasing, the only time it changes are at horizontal tangent lines. What's the shape of this curve going to be? A W, right? Right? So couldn't I theoretically get to a graph of this function?
Yes.
But I would need not only the x's, what else would I need? Y's, and I would plug into the original and then plot those points, true? Now wait, if I graph my W, is there anything special happening at negative rad 5, 0, and rad 5?
That's where it changes.
It's where it changes, and where it changes, think about section 3.1, extrema. There are going to be relative minimums and relative maximums. Without even learning any sort of forever card, can you guys look at that sign chart and tell me who's who? What's going to be occurring at negative rad 5? Why is it a min?
It's going down.
It's going
It's
down.
going down, then it's going up. The point exists where it changes. It's a critical number. It has to be a relative minimum at x equals negative rad 5. If they wanted the point, I could plug in to get the y, but blah, blah, blah. That's too complicated for right now. Are there any other relative minimums? Why? Because f changes from decreasing to increasing at a point that exists, or the derivative changes from negative to positive. Guess what? That's a forever card that's coming, but can you logically see why it's true? So what's going on at 0? Now, Why did I show you that? Pause. Give me just a second. Because, oh hey, look, there he is. There's something called the first derivative test for relative extrema, but all it says is, where do mins and maxes occur? That's all we have to do tomorrow to finish up section 3.3. We're going to practice it, and then I have a special activity to see if you really get it. Bye, guys! Yeah, definitely start homework. You can probably get through at least half. It'll work.
But I gotta figure out.
There's an argument today. It was like as a general announcement, but it was just for Argentina and Chile. I checked this in New York. Oh, I actually was going to ask you about that. Was that for your homework, Andrea? Yeah. It was like one of the, I think it was one of those you showed me later, and I graded it, and I didn't write it down. Okay. Can I speak at your spiral real fast? Yeah. That's why I had you guys check on grades. Chapter 2.
Good strawberry.
Brendan, what's up, bud?
I'm about the 18th.
It was given out on Friday, and I asked anyone who is absent to go get it from the front door. Go ahead and go to your train. It happens tomorrow. It's not the big pile of papers, it's the small pile. I'll also take it tomorrow. We're going to listen carefully to us, okay? And when you work on other stuff besides math, make sense of it.
Well,
It's your personal choice. It's your personal choice. So go ahead and get it. Brendan, I'll give you till tomorrow, okay?
I passed. Wait, we're getting it back today.
Okay, Joe.
We're getting it back.
Yes.
Pass.
Not yesterday. Congratulations! I thought you were talking about a test.
Oh yeah. We failed on the test.
No, come on, I was reason chapter 2.
Oh yeah. I was eating during class.
Chapter 2 you did. Okay. Can I this and you can get it during lunch?
Why are you having that
And I'll grade the other one. Do you remember why? Do you remember why?
Yeah, they did.
You're back.
So there's
Yeah, there's no way. Wow, it's warm in here.
Literally? It's warm, but it's this way.
Yeah,
90.8.
What are you talking about? Look at this.
Oh, Maddie did it.
And then it's like, Nathan, ready for this?
cheaters.
Look. And they both get far. It's not even possible to get 0. So
Puppy. For $30.
no, it's exactly
30 bucks. I said curb stomp a puppy for $30. That's
That was so messed up.
$30 is. It is. It's such a good deal.